Despite its importance, choosing the right kernel to use can be a difficult task. Luckily, the twinLab library comes with a very powerful feature which automates the process of kernel selection and composition. Welcome to digiLab, I'm Anna, and in today's video we're going to explore autoML in twinLab. By the end of this video, you'll gain a comprehensive understanding of twinLab's autoML functionality and learn how to effectively utilize it for Gaussian process modeling. Make sure to check out the full written tutorial that accompanies this video on the digiLab website. You'll find the link in the description below. Plus, you can download all the additional resources. Now let's break down what to expect in this video. In this tutorial, we explore Gaussian process regression using twinLab's default kernel, the Mattern kernel 5.2, applied to random data points. We will also explore all the kernels and how this affects the quantification of uncertainty and evaluation metrics. We will illustrate how to use autoML to automatically select the kernel, aiming to enhance our regression outcomes. This will provide insight to the efficacy of using twinLab's autoML with Gaussian process modeling. You can learn more about twinLab's capabilities and request a demo on our website. You can also learn more about Gaussian processes and the different kernels that exist, their advantages, limitations, and applications in part 1 and 2 of this course. So without further ado, let's start learning. And don't forget to subscribe so you don't miss any data science and AI adventures. Let's get started. Right, so first of all, we need to import the required libraries. So these are going to be NumPy, Pandas, Matplotlib, and twinLab. You will need to set up an API key. Remember not to share your API key publicly in your code or any public repositories to maintain security. Okay, so for our first example, we're going to generate some data points, and we're going to define a function called oscillator, which models a sinusoidal oscillation with some added linear component. The function takes an input x and returns the result of a cosine function multiplied by a sine function plus a linear term. After defining this function, what we're going to do is we're going to create a range of input values using numpy.linspace from -15 to 15, and then we're going to generate the corresponding output values by passing these input values through the oscillator function. Next, we're going to generate random data points with the range of -10 to 10 and calculate the corresponding output values using the oscillation function. Finally, what we're going to do is we're going to visualize the true function using a solid line plot. We're going to do this by using matplotlib.plot and overlay the randomly generated data points as scatter points using matplot.scatter. And this is how our plot looks like. Just keep in mind that because we're generating random data points, your results might differ a little bit. Now we're going to transform our random data points into a data frame. twinLab requires our data to be stored in a data frame, so we are converting the generated random data points into a pandas data frame. This function takes a dictionary where keys are column names and values are the corresponding data arrays. In this case, we're creating a data frame with two columns, x and y. The x column is going to contain the random input values and the y column is going to contain the corresponding output values. And we're going to display the first few rows. That's to check that our data frame has been created successfully, and we're going to call this data frame df. To display the first few rows, we use .head, and this is how our first rows of our data frame look like. Now we're going to upload the dataset to the cloud, and we need to do this so we can utilize our data. So for that, what we're going to do is we're going to assign a string that I'm going to call example data to the variable dataset_id. And this string, what it does, it represents the identifier for our dataset. Now what we do, we create a dataset object using .dataset in twinLab, and we pass dataset_id as an argument. And now is when we can upload the dataset to the cloud. So the dataset that we want to upload is represented for this data frame that we have created called df, and what we do is we use the upload method to upload this data frame to the cloud. And we're using variables equal to true, so we can see detailed information about the uploading process. So when we run this, what we get is an output that says that the data frame is uploading, processing the dataset, and finally the dataset example data was processed. Now we're going to run a Gaussian process without using autoML. We're going to run it first with the Matern kernel 5.2. This kernel is the default kernel for Gaussian processes in twinLab. If you want to know more about this kernel, go check out part 2 of this series. So first we set the identifier for our emulator by assigning the string basic GP, for example, to the variable emulator _ID. Then we need to create an emulator object using twinLab. For that we use the .emulator constructor and pass the emulator _ID as an argument to initialize the emulator. Now what we're going to do is to define the training parameters for the emulator. For that, what we're going to do is to use .train parameters. And we're going to set the ratio of training to testing data to 0.75. And that is the data that we'll be using for training. So 75% of our data is going to be used for training, but you can use this as you want. And then we are going to specify that we want to use the Gaussian process regression as the estimator. We're going to train the emulator using the train method of the emulator object. We're going to provide the data set that we have prepared earlier, and we're going to specify the input features as X and the output targets as Y, the training parameters, and we set variables to true to display detailed information about the training process. This process allows us to create a model that can predict output values based on input features using Gaussian process regression. The output that we get is that the model basic GP has begun training, and then when the training is complete, we receive a message saying that the training is complete. Now it's time to visualize our results. We're going to use the method plot to plot the data using the columns X and Y from our dataset. And we're going to set the limits for the X-axis from -15 to 15. Next, we're going to add the training data points to our plot. We're telling the plot to scatter the points from our data frame, and we're labeling these points as training data and coloring them to black. We're also adjusting the size of the dots to be 10 pixels, and we're adding a legend to the plot to explain what their data represents. After that, we're setting the title of the plot to be emulator inference results. And finally, we're just displaying the plot, and this is what we get. So what we can see is that there is a minimal uncertainty around the training data points, indicating high confidence in the model's prediction within the observed data range, but there is a big increase in uncertainty outside these data points. So this high uncertainty observed outside the data points indicates the model's limited confidence in predictions in these regions. After running the emulator, it's essential to assess its performance with appropriate evaluation metrics. twinLab provides a convenient method to accomplish this task, which is the emulator.score. By default, this function calculates the mean square error, offering insights into the accuracy of the emulator predictions compared to the actual data. So to evaluate the performance of our emulator, as I said before, we're going to call emulator.score after training the model, and this is going to provide us with a quantitative measure on how well the emulator is capturing the underlying patterns in the data. And this is the output that we get. So despite the observed uncertainty outside of the training data points, the mean is actually quite low. So what this suggests is that on average, the square difference between the model's prediction and the actual data values is extremely small. Let's try all the kernels and let's see what happens. So in certain scenarios, it's good to pre-select the kernel for the Gaussian process used in modeling. This could be due to the user's prior belief about the nature of the underlying process, such as assuming linearity, accounting for periodic behavior at varying length scales, or explicitly addressing short time noise in the data. The emulator class in twinLab offers a solution for this by providing the argument covariance module within the estimator parameters. Currently, the available kernels are represented as 3-character uppercase strings, each serving a specific modeling purpose. Users can compose kernels using brackets or the plus or asterisk string operators, allowing for more kernel combinations. Let's see what happens when we apply the linear kernel to this specific example. Okay, so we're going to follow the same steps. We're going to initialize the emulator, and then before defining the training parameters, what we're going to do is to define the estimator parameters with a covariance function. And in this case, we're going to choose the linear kernel. Then, same way as we did before, we define the training parameters for the emulator, and then we train the emulator. Finally, we plot our results, and this is what we get. We're also going to see what the mean square error is using dot score, and we get an output of 0.25, 29, and so on. As anticipated, right, because there's no that much linearity in our data, we can see a significant band of uncertainty, and the mean square error is actually quite high. This is because the linear kernel operates under the assumption of a linear relationship between the input features and output values, which we don't have in this example. And because this assumption doesn't hold true, the model struggles to capture the underlying patterns in the data, resulting in a less precise fit and a higher quantification of uncertainty. Let's move now to the matern kernel 1.2. But before that, in order to streamline our workflow and in order to avoid code duplication, we're going to create a function that allows the user to select the kernel. This function also generates visualizations of the emulator inference results and provide performance metrics. This way, we can efficiently train multiple models with different kernels while maintaining a clear and organized code structure. So let's see what happens when we choose the matern kernel 1.2. So in this case, we observe a presence of uncertainty surrounding certain training data points, along with a lower mean square error. This compared to the linear kernel. So this reduction of the mean square error compared to the linear kernel suggests an improved fit of the model to the data. Despite the presence of some uncertainty around the data points and decrease of uncertainty outside of the training data points, this kernel demonstrates an enhanced capability to capture the inherent complexities within the data, resulting in more accurate predictions and reduced error compared to the linear kernel. Let's move now to the matern kernel 3.2, and when we run our function choosing the matern kernel 3.2, this is what we get. So what we see is further reduction in the quantification of uncertainty around the data points, and also with an even lower mean square error value. This significant decrease in both the uncertainty and the mean square error compared to the matern kernel 1.2 indicates an improved fit and predictive accuracy of the model. We're going to try now the periodic kernel. So now we see a decrease of quantification of uncertainty around the data points, and we get a lower mean square error. So this was kind of expected, right? Because the periodic kernel is specifically designed to model periodic patterns in the data, making it highly effective at capturing repetitive trends or cyclical behaviors, which is what we have here in this example. As a result, the decreased uncertainty around the training data points indicates a higher confidence in the model predictions, with the model exhibiting a stronger alignment with the observed data. We're going to try now the radial basis function, and what we can observe is a significant band of uncertainty surrounding the training data points, and also a very high mean square error. So the large band of uncertainty indicates that the model lacks confidence in its predictions, especially in the regions of the input space where there are no or few training data points. And also a higher mean square error suggests that the model's predictions deviate from the actual data values, indicating a less accurate fit to the underlying patterns in the data. Finally, we're going to use the rational quadratic kernel, and we can see a significant decrease in uncertainty around the training data points. However, there is more uncertainty outside of training data points, and the mean square error is quite low. Now it's time to explore AutoML in twinLab. This feature autonomously identifies the optimal kernel for your dataset. With twinLab, users are relieved of the need to manually choose a kernel, and instead the platform utilizes sophisticated model selection techniques to choose the kernel that most suitably aligns with the data. So what we're going to do is we're going to initialize an emulator object specifically for AutoML, setting the identifier for this emulator as autoML GP. We're going to specify the parameters for the kernel selection process using model selection parameters. This includes setting the depth parameter to 4, controlling the maximum number of compositional kernels to search for, and then the beam parameter to 2, which controls the number of successful trials carried between search iterations, and the seed parameter to 123, which allows for reproducibility. We define the training parameters for the emulator, specifying that we want to enable model selection. And in order to do this, what we do is to set model selection equal to true, and we also provide the model selection parameters that we defined earlier. Additionally, we set the train test split ratio and the estimator to be used, in this case, Gaussian process regression. Finally, we train the emulator using the train method, and we set variables to true to display detailed information about the training process. We run this and we get an output saying that the model AutoML GP has begun training, and when it's completed, we get a message saying that the training has been completed. But how do we know which kernel has been chosen? Well, we can use emulator.summarize for this. This is the output that we get, and if we look here, we can see that the covariance model is an additive kernel of a periodic kernel, and linear kernel, and a radial basis function kernel. Now, the same way we did before, we're going to visualize it using plot. And in the plot, we can see a clear alignment between the predicted data points and the underlying function. This suggests that the model's prediction closely matched the actual data, even in regions where no training data was available. And the quantification of uncertainty is actually the lowest we have seen so far. So the lack of noticeable uncertainty around training data and the much lower uncertainty in regions with no training data suggests that the model is making predictions with high confidence and precision. So remember that Gaussian processes are probabilistic models that not only provide point predictions but also estimate the uncertainty associated with those predictions. When the uncertainty is not noticeable, it implies that the variance of the predicted distribution as estimated by the Gaussian process is low. In other words, the Gaussian process is confident in its predictions and provides output that closely follow the underlying function, even in areas when it was not explicitly trained. This indicates that the Gaussian process is effectively capturing the underlying patterns and relationships in the data, allowing it to make reliable predictions across the entire input space. This plot suggests that the Gaussian process model is performing well and is able to make accurate predictions with high confidence. And same as we did before, if we want to assess the emulator's performance, we use .score, and what we get is the lowest score that we've seen so far. This indicates that our model's performance is excellent, demonstrating minimal deviation between the actual target values and the predictions it generates. I think we can conclude that our Gaussian process model using AutoML effectively captures the underlying patterns in the data and makes highly accurate predictions. Finally, let's talk about deleting the emulators and the dataset. Deleting these objects allows us to ensure that no unnecessary resources are retained in memory or storage after we've finished using the emulators and the dataset. And this practice helps optimize resource usage and prevents memory leaks. To do that, we use emulator.delete and then model selection emulator.delete. And then for the dataset.delete. And this concludes our Gaussian Processes series. Let me know in the comments what was your favorite part and what would you like to see next. Don't forget to like and subscribe to stay updated with our upcoming content. Make sure you download the video resources on the digiLab website, when you can also find more courses on data science and AI. You can also find the written tutorial link in the description. Thank you so much for joining me in this adventure. I can't wait to see you in the next one.